Ever, of course it's right where I want to reference. The theorem says that, hey, let's say that you can look at it like this. You're trying to figure out what a sequence A sub n does, right? So you take its absolute value and you figure out that it goes to 0. That means that that sequence without taking the absolute value also goes to 0. So we were looking at this sequence -1 to the n over n. We were like, where does it go? So we took its absolute value. We figured out that that goes to 0. And that means that the sequence without the absolute value must also go to 0. Okay? This is a very useful theorem when you have this -1 to an n power. Because that -1 to the n power will always become a 1 when you use this theorem. Agree? Okay, let's try another one. How about this one? What about the sequence? Well, yeah, let's just look at the sequence -1 to the n. Wait a minute. We looked at that already, didn't we? We looked at that already. So I'm asking the question, does this converge or diverge? We already said this diverged, right? But let's try using the theorem. Let's take the limit as n goes to infinity of the absolute value of this, right? Well, that's the same as the limit as n goes to infinity of what? Of 1, right? Because this doesn't matter, right? 1 or -1, when I take the absolute value, I get 1. So what is the limit as n goes to infinity of 1? N's not in here, right? So that's just 1. So what does that mean? Does it converge to 1 then? We said it diverged. Wait a minute. This theorem is junk. No? What's going on? Read the theorem. Read the theorem. Okay, there we go. All right. You must be careful with theorems, right? The theorem says very explicitly that if you take the absolute value of the sequence and take the limit and get 0, then the answer is 0. This theorem does not say if you get L, then the answer is L. Okay? So because that limit was 1, means this theorem does not apply.
Wait, so how do you know?
Okay?
I guess that wasn't a question for the last example that we did. Like, how do you know, yes, I have to use this theorem? Like, all of them that we...
Nothing really tells you you had to. I could have done it with the squeeze theorem. But the fact that it had the -1 to the n power made me want to use this because taking the absolute value of -1 to the n turns that into 1 all the time.
So do we only use the absolute value with that over something, like the -1 to the n?
If you see a -1 to the n, I would be thinking this. It may not work because you might get, like on the last problem that I just did right now, we got 1 is the answer, right? And if I get 1, then I can't use the theorem. It has to go to 0. Yeah, I mean, it's a tool. You have a tool in your toolbox, okay? You might need it, you might use it sometimes, you might not.
So then would it be wrong to say, like, with the -1 to the n over something, I could immediately think, like, it's safe for me to use this theorem because of the over whatever?
I would try this theorem, yeah, because if you have -1 to the n over something that's getting bigger, then you know that's going to probably turn into like 1 over something that's getting big, and that's going to go to 0, and then the theorem would work. Yeah.
And there wouldn't have been a way to use the squeeze theorem on that?
Yes, you could have used the squeeze theorem. Because you could have started out and said, look, -1 to the n is always between 1 and -1. I mean, it is either 1 or -1, right? But that would be true to say that, right?
Yeah.
And then you just divide by n and divide by n and divide by n, and then take this limit, they both go to 0. Right? You could do that also.
They both go to 0. What does that mean? So what does it means? Wouldn't that mean it converges? They both go to 0?
Yes. That wasn't the problem we just did.
Well,
No, I did -1 to the n. That one diverged. I thought you were asking about this one.
no. I was talking
Oh, okay. Yeah, then if you did this one, the most you could do is this, right? But then this is the actual sequence. So if you say, what's the limit of this as n goes to infinity, you'd say 1, right? What's the limit as this goes to infinity? -1. They're going to two different places, right? So that means you have not squeezed it. You have to be able to squeeze it in order to use the theorem.
So
Okay.
in that case, like you're saying that we could have used Lee's theorem or the Sub N theorem, can we just use Lee's theorem, or is there going to be a time where we have to use this one and you won't
I
be
think
able-
this is more important than the squeeze theorem.
Really?
Yep.
It's just like
Yeah.
it's like,
Okay, so I know what you're saying. You feel a little uncomfortable with the idea that you're not quite sure when to use this, and get used to it. Because honestly, because this is what this is about to be about. The major problems of this chapter are going to be, I'm going to give you something, and I'm going to say, tell me if it converges or diverges. And that's all I want to know. I don't even want to know what it converges to. I just want to know if it converges or diverges. And to do that, you're going to have to figure out one of like 8 different ways to approach it. Okay? And then not only that, you're going to have to, well, you're just going to have to see this, but it's not going to be about whether or not you give me the right answer. Like converge, yes, you got it right. You actually have to prove that it converged with logical steps that follow theorems, and this starts to get kind of mathy at this point. It's going to get really, it's what makes chapter 8 difficult, all right? But just for now, hang tight. Just understand this is a tool in our toolbox, and we'll start to, when you do the homework, you'll see where we use it. And all right, let's look at the next one. Let's look at the next one. So this is a specific result. It says, look, let's say that we have a sequence r to the n. So what I mean by that is, let's say our sequence is like a sub n equals 3 to the n, or a sub n equals 1/2 to the n, or a sub n equals pi to the n, or a sub n equals 0.75 to the n. Okay, these are all sequences that have this pattern of some number raised to the n. Do you all agree? This theorem, not this theorem, this says that if the absolute value of r is less than 1, it's going to converge to 0. So does this converge to 0? Yes. Does that one converge to 0? Yes, because this number's absolute value is less than 1. What if I made that negative? Still converge to 0. Doesn't matter. If the absolute value of that number is less than 1, this converges. You can see it by just think about what this sequence right here looks like. It's 1/2, 1/4, 1/8, 1/16, right? That's what's happening with this one. And so that's basically 1 on top, and the bottom gets bigger, goes down to 0, right? Same thing would happen here. It would be switching between positive and negative, but they'd be getting smaller. Now that leaves for us to figure out what would happen to these two. So what do you think about that, those two? If the absolute value of r is bigger than 1. Think about what that sequence would look like. What would this sequence look like? 3, 9, 27, 81, ... right? What's happening to that sequence? It's blowing up, right? It's growing, exponentially growing, isn't it? So it would diverge. So we could actually say that here, that if the absolute value is greater than, we can put that here. If the absolute value of r is greater than 1, it diverges. And what if r is 1? What if r is 1? It'd be 1 squared, 1 cubed, 1, 1, 1, 1, 1. So it would converge to 1. So if r is 1, then it would converge to 1. Because basically you're looking at 1 to the n, right? That sequence right there would converge to 1. Okay, you all good? All right, I think we're ready to shift gears a little bit. We're going to go to the back page of the notes and talk about some other things here. that absolute value, hold on. We said if r was equal to 1, right? If r was equal to 1,
No, I'm saying if it's negative 1, if it's less than 1, then that'd be equal to 0, right?
no, but it's the absolute value, right? Didn't we just say if the absolute value of r is less than 1, it converged? If the absolute value of r was bigger than 1, it diverged. If r equals 1, we said it converged. But what if r is equal to negative 1? See, negative 1 is not this or this. Right? What is the absolute value of this? 1, right? That's not this or this. So this would be its own case, but we already showed that that diverged. Right?
Because I remember you saying negative 0.75 is still less than 1.
That is, yes. Negative 0.75, the absolute value of it. So the r, this is r, right? This is saying if the absolute value of that is less than 1. So the absolute value of negative 0.75 is 0.75, which is less than 1. So that would converge.
And I was saying if it was the absolute value of negative 1, it'd just be 0.
It would be 1. It'd be 1, right? We are saying that if the absolute value of the number is less than 1, so it's not this. Absolute value is greater than 1. It's this, right? If r is 1, not absolute value of r is 1. If r is 1, it converges. And if r is negative 1, it diverges. I think you're trying to fit this into one of these cases, but it's not. This is its own case. Does that make sense? All right. Some new definitions, but you've seen these in Cal 1. They just have a sort of a different sort of notation to them. A sequence is said to be increasing if it looks like this. And that should make sense to everyone, right? If you read it from left to right like a book, the dots are going up. But technically what that means is this, that if you go out here and you pick some point in the sequence, let's say that's a sub n, you plug in whatever n is and you get that point, right? The next one next to it is a sub n plus 1. That one should be slightly higher than this one, right? And that's what this inequality is saying. To be increasing, a sub n has to be smaller than a sub n plus 1. So this is the one in front of this one, right? This one in front has to be lower than the one to the right of it. That's what that inequality says. That's what you need to be increasing. Now decreasing, the only difference is that that inequality flips over, right? Because you need it the other way around. You need that the nth one be bigger than the next one. So the nth one has to be higher than the one following it. If that happens, then it's going to start to drop like that, and you have decreasing. That make sense? Sure?
What if
Okay.
it's just a really close-up view of a parabola? So
What
it's
if-
about to like start increasing.
Well, then it wouldn't be an increasing sequence. The only way you can say it's decreasing is if this inequality holds all the time.
Okay.
Right? So if it holds for all n, then it's a decreasing sequence.
Okay.
Right? So a parabola-looking thing would not qualify as being decreasing. Now, it'd be decreasing for a little while, but then it would start increasing. Okay, in either case above, whether or not you're increasing or decreasing, if you're one or the other, and you don't have to be one or the other, you can have sign, right? That doesn't increase all the time or decrease all the time. But if your sequence is increasing or decreasing, in either case, we call it a monotonic sequence. So monotonic sequences are sequences that are either increasing all the time or decreasing all the time.
It's just because it's always going like one or the
In one or the other, like mono meaning one, right? Tonic meaning water. No, tonic water? No. Monotonic meaning doing the same thing for the whole time, all right?
So like just like any linear function.
Like a linear function would be, if you turn it into a sequence, would be an increasing, monotonically increasing function, sequence. All right, now, increasing is one thing. We have another definition which has to do with something called being bounded. So what we want to look at, when we look at boundedness, we want to think about like a ceiling and a floor. All right, so if we have a sequence, we will say that the sequence is bounded above if there is a number, capital M. such that our sequence is always smaller than or equal to capital M for every n greater than or equal to 1. So that means if we draw our sequence, the sequence always stays below, or it could touch the m, but it cannot go above it, all right? Then that m would be what we call an upper bound, and we would say the sequence is bounded above, all right? It doesn't have to be a limit. I was just about to say this. I was going to ask you, is m unique? So look at this sequence right here. This sequence is what type of sequence? It appears to be, in reference to the previous two definitions, monotonically increasing, right? That's what that appears to be. So let's say that this sequence had a limit. Let's say the limit of that sequence right there was L. Is it bounded above by M? So L appears to be an upper bound, right? But it's not the only upper bound. Any number above it would be a ceiling. So this M is not unique. It's any number that the sequence never gets to, okay? So if your sequence flattens out towards L, then L plus 1 would be an upper bound, right? L plus 2 would be an upper bound. Any of those, right, if you have any number that it never gets past, going up, right? If it never goes up past a number, then that's an upper bound, but we would say that the sequence is bounded above, all right? Now, the same thing goes the other way around. If the sequence if there's a number, little m, okay, little m, such that our sequence is always above or possibly touching that m for all the n's, all right, so over our entire sequence, we have a floor, right? So that would be like the floor below my feet. That would be a lower bound. But the floor below this floor, right, the second floor, would also be a lower bound. Any of those would show that the sequence is bounded below, right? So again, it doesn't have to be the limit. Now, you know how we said if you're increasing or decreasing, we call it monotonic? Yeah. Increasing or decreasing, we call it monotonic. If you are bounded above and bounded below, and, not or. If you're bounded above and bounded below, then we will say that you are a bounded sequence. So if I say, hey, we've got this bounded sequence, what I'm telling you is that it's got a ceiling and a floor, okay? Not one or the other, both. With me? Yes. Like sine of n. Yeah. It's bounded above and below, right? Mm-hmm. Okay. So sine of n is a bounded sequence. Now it diverges, but it's a bounded sequence. Agreed? Sine of n is a bounded sequence that is divergent. That all leads us to the last very important theorem, which is called the monotonic sequence theorem. And the monotonic sequence theorem says that every bounded monotonic sequence is convergent. Every bounded monotonic sequence is convergent. This theorem does not tell you anything about what the sequence converges to. All it tells you is that if you can somehow prove that your sequence is bounded, that means above and below, right? And show that it's monotonic, which means that it's either increasing or decreasing, then you can conclude from that it is convergent. All right? So this is, you know how you were feeling a little uncomfortable a little while? Okay, this is really going to be the first thing that I do in this class, I think, where it's going to feel, I think it's going to feel like different, all right? Because we're going to use the theorem to prove something. I'm going to give you a sequence and we're going to use the theorem to prove that it converges, all right? So it's going to seem different right now, but get used to it. All right, here we go. Let's see if we can't do a visual proof of this theorem. Can we not convince ourselves that this is true? So let's say we have a sequence that's bounded. All right, that means that there's a ceiling and a floor that my sequence can't go past, right? And then let's make it monotonic, which means that it has to be either decreasing or increasing, right? So you pick one. What do you want? Decreasing? Okay. So what we would do let's say, and this doesn't matter where it is, but we would first plug in 1, right? We plug in 1 into our sequence, it's going to spit a number out. Now I know that number has to be between here and here, right? So I'm just going to slap it right there. Now, when I plug in 2, that answer has to be between those 2 red lines, but also, because we said it's decreasing, it must be below that one, right? So it's got to be lower than that. And then we go to the next one, right? 3, it's got to be a little bit lower than that. So this thing continues to decrease, right? How do we know that it has to converge then?
Can never touch it.
I can't go past this, right? And if I can't go past this, then it needs to have a limit, right? It needs to have something it's approaching without ever getting there. So it has to have some sort of, like, you could look at it as almost like a horizontal asymptote. I have to have some limit it goes to. Now that limit, again, doesn't have to be down here, but it has to have a limit. Now why can't it turn back up?
Because then
It won't be monotonic, right? The monotonic forces us to keep going down, but this right here forces us to never go past something, which means we have to flatten out. Now, could we do this? I'm sorry, these are too close. Could I have gone below it and then I couldn't go back up and just oscillate on it, right? Because then it wouldn't be monotonic. So it has to, like, asymptotically approach something. Yes?
Is inverse tangent one? Or no?
Arctangent? Yeah?
It is, right?
Arctan of n.
Oh.
Yes, if you define the arctangent function on the natural numbers and graph it, you would have a bounded monotonic sequence. Yep. There's a lot of bounded monotonic sequences. All right, you ready to see how we could use this theorem? Okay. The important part of this problem, all right, I'm going to put the sequence up here. Let me put it up here first. Then I'm going to say something really important. Which one do I want to do? Okay. Show that A sub n equals 2n minus 3 over 5n plus 1 is convergent using the monotonic bounded sequence theorem. Does anybody have on the, on Canvas, I gave you a bunch of formula sheets that you can use throughout the semester. Does anybody have the full set of those right now, by chance? Like easily accessible? I want the one that says convergence test for series on it. There it is. Perfect. Thank you. If I could borrow this. Okay, so here's what I need to make clear. If I give you this sequence right now, and I ask you, does that converge or diverge? Could you do this using switching it to f of x, taking the limit, and then using L'Hopital and being done? Yes. Okay? So I'm going to do it. I'm going to show that it's convergent using the monotonic bounded sequence theorem. When I'm done, I do not want to hear the question, could we have just done it with the limit and that would have been easier, so why not just do it that way? You know what I'm saying? Like, I understand we could do it easier another way. The importance of this is for you to understand how to write things down logically when you're trying to prove something, because this table right here that you're going to be allowed to have on your next test basically is a bunch of things like the monotonic bounded sequence theorem, where it says something like, okay, you have this certain thing, it looks like a certain thing, here are the things you have to show are true. Okay, so like for this I have to show two things. I would have to show this sequence is bounded, and I'd have to show it's monotonic. If I can show this is bounded and monotonic, I'm done, right? That's all this sheet is about. It's about you're trying to show something. So, or you're trying to prove something, so you have to show this or this. You have to show this or this. And it's like, you know, this is what you'll do, and if that happens, then it's convergent, and if this happens, it's divergent. So it's a process. Each one of these problems becomes a process of logical steps. And at the end, it's like a coin flip. It's, you know, it's converge or diverge, but it's all about the process in between is what's important to me. So as I do this, please recognize how I'm stating things, how I'm like putting my thoughts down on paper, because this is the important part, all right? All right, so here we go. First thing, I want to show, so I'm writing this as if I want somebody to be able to read this and kind of understand what I'm doing, all right? I want to show two things. One, A sub n is bounded. Two, A sub n is monotonic. Right? If I can show 1 and 2, I'm done. Agreed? Because that's what the theorem says. The theorem says if you're bounded and monotonic, you're convergent. Okay, so let's start on number 1. Now, see this want to show? I'm going to abbreviate that WTS. And a lot of mathematicians, they do that. Okay, it's not just me being lazy. You see that sometimes in books. Okay, WTS. All right, I want to show. So let's start with number 1. 1. I want to show that A sub n is bounded. That implies that there exists a capital M such that our sequence is always less than or equal to capital M. What is that again? What's the capital M? Yeah, so I have to show it's bounded, which means I have to show it's bounded above and below, right? So to say that I want to show it's bounded means that I need to show that there exists some capital M where my sequence is always smaller than that number, right? Also, there exists seems like it would become a pain in the ass to have to write that over and over, right? So in mathematics, we actually have a symbol for that also. It's a capital E backwards like that. That stands for there exists. It's just it's just because it's like it becomes a language, okay? It becomes a language. Yeah, you get tired of writing all these things down. You're writing symbols anyway. You may as well make up your own. I'm not making this up. That's a symbol for there exists. So we want to show that there exists a capital M such that this is true, right? And we want to show that there exists a little m such that st such that A sub n is bigger than or equal to little m.
I don't even know where we're anymore.
The M over here on the top line, that's a lowercase?
This is capital. I'll stress it more. Capital. There. Let's do that. Capital M. Little m. Y'all know this right here. The limit as x approaches a of f of x equals L, like that, right? That's the standard notation for saying that the limit of a function approaches L, right? Okay. I'll show you what's called the precise definition of that, all right? The precise definition of that says, for every epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of x minus a less than delta implies that the absolute value of f of x minus L is less than epsilon. There we go. So that looks very mathy, doesn't it? Doesn't that look like mathy to you? Like really mathy? But it's just a sentence. For every epsilon greater than 0, there exists a delta greater than 0 such that when the absolute value of these two are less than that delta right there, that the function's value minus its limit is less than that epsilon.
What's epsilon?
Any positive number. Don't worry about the meaning of the definition. What I'm getting at is that that's the way mathematicians write, okay? This is the way we write. It's like a little language, but a lot of it's just abbreviations, okay? So this means for all, for every. There exists, right? Such that. I'm just showing you some of the notation. There's nothing wrong with it, right? Don't make it worse than it is.
This process that we're going to be doing, it
Yeah.
kind of sounds like we already figured out whether or not it's monotonic and bounded.
Wait, this process?
Yeah. Like, well, I mean, we're not going to do, like, what if we get a problem? We come across a problem and it's not monotonic.
Hey, hold on a second. Don't look at it that way. I'm not trying to force mathematics on you. I'm just trying to share with you the language. Don't stress out. Don't stress out. Don't stress out. Look, this is just what is so difficult about understanding that these two words is that symbol. It's just an abbreviation. Okay, well, let me finish stressing you out because I'm not done. All right? We haven't even done anything yet. It's not as bad as you're making it out to be. It's not. Yeah, let's get to it. Let's get to it. All right, I've got to show these two things, right? Got to show these two things, and I've got about 9 minutes to do it. All right, so what I'm going to do next is on the side here, I think what I'd like to do is just list out the first few terms of the sequence, just to get an idea of what it's doing. All right, so if we plug in 1, what do we get? -1 over 6. And then the tops are going to jump by how much each time? 2. And the bottoms are going to jump by 5. Okay. So it's going to be jump by 2, you get 1 over 11. And then it's going to jump by 2 again, so 3 over, and then add 5 to that, 16, and so on and so forth. We'll do one more, 5 over 21, ... Okay, so now what we need to do is make a guess, okay? Make a guess as to a capital M that we think is bigger than this thing all the time. Anybody have a guess as to a capital M that would make that? That's always been 1, okay? 1 seem reasonable. Doesn't seem like these are ever going to get to 1, right? Okay, so I needed to show that it was bounded. So I needed to show that there exists some capital M that's always bigger than it. I also need to show that there's a little m that's always smaller than it. So now I need to go find those numbers. We think that capital M can be 1. What about little m? We can't use 0, right, because this is a negative number. But it looks like after this one, they're all positive. So -1 seems like a good candidate. Agreed? Does that make sense? Okay. So I'm continuing here. I'm continuing. So now what I get to do is I need to now let capital M be 1 and little m be -1. Okay? Now let me try and see if the two things I needed to show are true. And I'll just do them side by side. The first thing I had to do was show that my sequence was always less than capital M, right? Okay, and then the other thing I needed to show was that my sequence is always bigger than little m. Right? These are the two things. So this becomes a question. Is this true or not? Is my sequence always less than or equal to capital M? And is my sequence always bigger than or equal to -1? Is it? Well, what's the sequence? 2n minus 3 over 5n plus 1, right? Is that always less than 1? Question. Well, now you get to just do some algebra. Start, trying to solve for n. This is a linear inequality, or it's non-linear, it's a rational inequality, but still we can do it. Why don't we multiply both sides by 5n plus 1? If we multiply 5n by 5n plus 1, we don't have to worry about flipping the inequality, do we? Why not? 5n plus 1 is positive, right? Because n is always 1, 2, 3, 4. So that's okay. How about we get all the n's on one side, all the things that are not n's on the other side? So what about we bring this 2n over here? So 3n, right? Bigger than, and then bring that 1 over there. -4. Divide by 3. Do you all agree with that statement? Is that a true statement? That's true, isn't it? I mean, for the n's we're talking about, right? N is 1, 2, 3, 4. And in general, n could be negative and this wouldn't be true, but for the n's we're referring to, that's true. So what we're doing is we could say, look, if you work backwards, if n is this, then that's this, and that's this, and that's this, and this is true, right?
Yeah.
So if this is true, that's true, and that means that this was a good candidate for m, and so I've shown that it's bounded above. Started with the statement I didn't know, I ended with a true statement, which means if we work backwards, that's true. Okay? Yes?
Shouldn't that number be the first number on our sequence?
No. N, remember, n is just, this right here is a sub 1, right? A sub 2, a sub 3. So if we go somewhere out here, that's a sub n, right? That would be the nth one. All this is saying is that we said, is our sequence less than 1 or equal to 1? And the conclusion is, well, yes, it will be less than 1 so long as you can guarantee me that the n you're using is bigger than or equal to this negative 4/3, right? And the n is always that, right? And that's always 1, 2, 3, so that's always bigger than negative 4/3. Make sense? Okay, now let's see if this one's true. Same exact setup. 2n minus 3 over 5n plus 1 is greater or equal to negative 1. Multiply both sides by 5n plus 1, but now they're going to become negative. And then move everything to one side. 7n on this side. And then over here, we come over, it'll be greater or equal to 2. And then divide by 7. Is n bigger than or equal to 2/7? Yes, because n starts at 1. So this is true, which means this is true. So what we have shown now is that our sequence is bounded. Agreed?
Yes.
Was that so bad? No. Okay. So now, therefore, right? After this, therefore, sorry, 3 dots means therefore. Therefore, a sub n is bounded. Okay, move on to number 2. Part 2.
So to see it's monotonic.
Yep. I erased the damn sequence. Okay. 2. Want to show a sub n is monotonic. Now, we listed out the sequence, didn't we? And it was like negative something, then something, then something. Do you think it's increasing or decreasing? I mean, it went from negative up to a positive, right? So if there's any hope, it's going to have to be increasing, right? I want to show it's monotonic. Moreover, no abbreviation. Moreover, I want to show a sub n is increasing, because that's what I think it's doing. And that's just by me looking at it. All right? I don't think it's a decreasing sequence. I think it's increasing. So what is it that I need to show? Therefore, I want to show, what did increasing mean again? I know visually what it meant, but I want to show that a sub n is less than a sub n plus 1, right? That's what I want to show, and I have like 2 minutes to do it, 1 minute to do it. Okay? That's what I want to show, right? I want to convince everyone in here that this is going to be true. All right, so let me show it. What is a sub n? 2n minus 3 over 5n plus 1, right? I want to show that that's less than a sub n plus 1. What's that? So remember, this is like a function, right? A sub n means plug n into that function. A sub n plus 1 means plug n plus 1 into that function, right? So isn't that 2 times n plus 1 in parentheses minus 3 over 5 times n plus 1 plus 1. Do y'all see how that's like, this is like f of x, this is f of x plus 1. This is a sub n, this is a sub n plus 1. Yeah? So like if I said plug 2 into this, you plug in 2, and then this would be plugging in 3. Now, I need to show that that inequality is true. Yeah, let's clean it up. 2n minus 3, 5n plus 1, less than 2n minus 1 over 5n plus 6. I'm going fast here. 2n, 2 minus 3. So that means minus 1. Then 5n plus 5 plus 1 is that. I'm running out of time. I'm out of time. I'm going to cross multiply. This is going to have the effect of clearing the fractions out. So I'm basically multiplying both sides of this inequality by the denominators. So multiplying this side by 5n plus 6, this side by 5n plus 6, and then this side by 5n plus 1, and this side by 5n plus 1, and basically all the fractions go away. And you have that, right? Now, distribute. 10n squared. 12 minus 15. I think I'm getting, wait, is that right? 12, take away 15. Minus 3n. And then minus 18. Less than 10n squared. 2n minus, so minus 3n again. And minus 1. You all with me? Okay, now, if we start trying to move things around, we're going to see that some good stuff's happening here. 10n squared and 10n squared go away. Plus 3n and or minus 3n and minus 3n go away because if we add 3n to both sides, they're gone, right? Same reason the 10n squareds went away. And then what are you left with there? Negative 18 is less than negative 1. Is that a true statement? Yes, it is, which means that this was true, which means that it was increasing. Therefore, a sub n is increasing. And therefore, a sub n is convergent. Okay. Sorry about that. Sorry that that took so long. Do your best with the homework for 8.1, all right? Do your best with 8.1 homework. And that's it, right? Don't think there's anything else. We'll come back. We'll start 8.2. And we have a test next Wednesday on everything we've done up through 8.1.